Hey, welcome to The Explainer. Now, for just a second, I want you to forget about all those crazy lines of code you see in the movies. Instead, I want you to think of computer science as learning to be a modern architect. But instead of building with steel and concrete, you're building our entire digital world with data and logic.
So, that brings up the big question, right? How do you build a digital world from the ground up? Well, just like any construction project, the very first thing you have to do is understand your raw materials. What are the digital bricks and mortar that a modern architect really needs to master?
All right, so any architect worth their salt knows their materials inside and out. For a digital architect, that journey begins with a pretty fundamental concept, the secret language of computers. And believe it or not, it's a language spoken entirely in zeros and ones.
Okay, let's get down to the absolute bedrock of everything. We're talking about the bit. It's the simplest thing imaginable, really. Just a tiny switch that's either on, which we call a 1, or off, which we call a 0. And here's the crazy part. Literally every photo you've ever taken, every message you've ever sent, it all boils down to billions and billions of these simple little on or off switches.
And look, this isn't just some abstract theory. It gets real fast. You can see it right here in this exam question. Students have to learn how to take these long strings of ones and zeros, that's called binary, and translate them back into the numbers that you and I use every single day.
Okay, so numbers are one thing. But what about, well, everything else? How on earth does a computer represent all the different letters, symbols, and characters that make up every single language on the planet, from English to Korean?
Well, the solution is basically a kind of universal translator for computers. An early system, you might have heard of it, called ASCII, used 8 bits, and that was great for English, but it just wasn't big enough for languages like Korean that have thousands of unique characters. So we needed something bigger. Enter Unicode. It's a 16-bit system, which gives us way more room to represent pretty much every character, emoji, and symbol you can think of.
All right, so we've got everything translated into ones and zeros. Now what? How does a computer actually think with this stuff? The answer is shockingly simple. It uses these tiny little decision makers called logic gates. So an AND gate, for example, is like having 2 light switches on the same circuit. You need both of them to be on for the light to turn on. It's these incredibly simple circuits, like AND, OR, and NOT, that are the real building blocks for every single calculation your computer ever makes.
Okay, so we've got our digital bricks and mortar. The next logical step, right? We've got to connect everything together. Let's take a look at the blueprints for building these massive digital structures that we all use, like the internet.
And just like in the real world, connections start local. A local area network, or a LAN, that's what connects all the devices in your house, or maybe in a single office. But then when you start linking all those LANs together across a huge area, you get a wide area network, or a WAN. And the internet? Well, that's the ultimate WAN, the big one that connects pretty much everything on the planet. Now, for all these billions of devices to talk to each other, they each need a unique address. Think of it like a mailing address for your phone or your laptop. The only problem was, the original system, IPv4, was like a small town that just completely ran out of addresses. So the solution was to build an absolute megacity, IPv6, a way bigger 128-bit system.
And when I say megacity, I mean the scale here is just mind-boggling. It's almost impossible to wrap your head around. IPv6 gives us 340 undecillion unique addresses. I mean, that is a number so big, you could give an IP address to every single atom on the surface of the Earth, and you'd still have addresses left over. It's a system built for a future where trillions of devices are all connected.
So, we have our materials, we've got our global network, but you can't just start throwing digital bricks around, right? A good architect needs a plan, a blueprint. And in computer science, that formal process for building things is called the System Development Lifecycle.
And this System Development Lifecycle, or SDLC for short, it's a really structured 5-step process. You start with planning, then you move into analysis to figure out what people need. After that comes the design, and then implementation, that's the actual coding part. And finally, you have ongoing support and security. It's the official roadmap to take a project from just an idea all the way to a finished, working, secure system.
And again, this isn't just something you read in a textbook. It's super practical. Take a look at this exam question here. Students are asked to think about the first steps for building a new app. Figuring out if it's even a good idea from a business perspective, and then they have to identify which phase that is. And that, of course, is the very first one, planning.
All right, and this last part, this might be the most important piece of the whole puzzle. Because being an architect of our digital worlds, well, that comes with a huge amount of responsibility. A really core part of learning computer science today is understanding the ethical rules that govern this new frontier.
And we're not just talking about one simple rule here. This is a whole landscape of really critical ideas. Students have to dig into the obvious stuff, like software piracy, but also much more complex challenges like information privacy, intellectual property, and even the environmental impact of our tech, which is sometimes called green computing.
And let me tell you, these rules are not taken lightly. Not at all. Academic integrity policies spell out in no uncertain terms crystal clear definitions for things like plagiarism. There's really no gray area about what's okay and what's not.
And once again, this stuff isn't just theory. You have to be able to apply it. It's a skill that gets tested. This question asked students to look at a very modern problem, somebody misusing AI to create fake images from a person's social media profile and identify exactly which ethical lines are being crossed. This is ethics in the real world, for sure.
So at the end of the day, what's the big takeaway? It's that learning computer science is so much more than just learning to code. It's really about becoming an architect. Someone with a powerful toolkit, yes, but also with a serious responsibility for the digital future we're all building together. And that really just leaves one question. What kind of world are we going to choose to build?